Even when the contents stay the same, rearranging them can make everything feel different. Think of your playlists, for example. The same songs, just shuffled, can change the vibe. So why don't we stop and discuss distinct objects to see what we can learn from them? Before we dive into calculating combinations and building structures, we should first examine how we organize items in mathematics. That brings us to one of the core ideas: sets. To understand how we organize things in math, we begin with sets. We often group items together like putting them in the bag. The items inside are called elements, and the bag itself is the set. Typically, we don't care about the order in which we place the items in the bag. We can shake our imaginary bags however we like. The same idea applies to sets. Imagine searching for a lost bag that contains a photo, business card, and a $10 bill. If someone finds a bag with the same items, just in a different order, you would still say that's your bag. Same items, different order. And unlike a real bag, a set isn't limited by space. It can even contain an infinite number of elements. Sets don't allow duplicates. They care only about whether something is in the set, not how many times it appears. The definition of distinct can be a bit ambiguous. Are two blue shirts distinct elements? What if one has a different size? Since what counts as distinct can be subjective, we need to define our sets clearly. We should be able to tell exactly which elements belong and which don't. A set of tall people is vague, but if we define tall as above 6 feet, it becomes well defined. We've now laid the groundwork for sets. They have the following characteristics: orderless, order doesn't matter; unbounded, can have any number of elements; distinct, no duplicates allowed; and well defined, clear what belongs and what doesn't. We could go deeper into this topic, but I'll draw the line here for now. Maybe we'll revisit it in a later video. Now that we have a solid understanding of sets, it's time to explore what we can do with them. That brings us to arrangements, selections, and permutations, which leads us into the field of combinatorics. I'm dividing this chapter's ideas into different levels or categories. Some you'll use all the time, others only in specific situations, but they're all useful when the right problem arises. Some even show up in daily life or at math Olympiads. Let's begin with the first one: sum and product rules. Consider purchasing a school lunch. There are 15 varieties of drinks and 10 varieties of toast. Every day you want a different lunch, with just one piece of toast and one drink. Many of you probably tried multiplying these numbers, 10 times 15, to get 115. Consider the drinks as a set D with 15 elements, and the toast as a set T with 10. Every lunch combines one item from T and one from D. Imagine a grid with rows for toast options and columns for drinks. Every cell represents a distinct lunch consisting of one piece of toast and one drink. This grid creates a rectangle in geometry. Its area 10 times 15 indicates that there are 15 possible lunches. But what if the question changed? What if we want to count lunches with either a toast or a beverage instead of both? How would that change our answer? In this case, we line up all the options in a row. The 10 toasts and 15 beverages. The total number of options is the sum. 10 plus 15 equals 25. We call these the product and sum rules. If the problem uses AND, we multiply. If it uses OR, we add. Permutations. Now we can start asking questions about the order, the sequence in which things happen or are arranged. Let's imagine all the different ways we can draw 10 cards, ace to 10 of hearts. We'll consider two approaches to this. We can select a random card from the deck, remove it, and repeat the process. This model is known as the selection model, where we select cards from a deck. Alternatively, we can choose a card and allocate it to a specific location, then leave the card there. This model would be the allocation model. Both approaches give us the same result, as we'll see. For our first draw, we have to pick one of 10 cards, and then we only have 9 cards to choose from. On the 9, since we draw this card and put it to the side, repeating this process, we lose cards until we run out of cards. So first 10 options, then 9, then 8, and so on down to 1. Since we use the word and, we should multiply. Multiplying these together gives 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, which equals 3,628,800 ways. That was selection. Now let's discuss allocation. Instead of picking location, we do it by selecting which card to place into a predetermined location. For the first spot, we can choose any of the 10 cards, and then we choose a second card from the 9 remaining cards and place it into the second spot, and then again from the 8 cards left, and so on, until we fill all the spots. Since I don't want to list all the numbers from 10 down to 1, we have a shorthand. 10. No, I'm not shouting in excitement about the number 10. When we say 10 factorial, written as 10 exclamation mark, it means multiplying every whole number from 10 down to 1. This calculation gives us the total number of ways we can allocate the cards to the spots. We call this problem a permutation. These cards were a permutation of 10 cards. However, its limitation is that we have to place down every card. What if we draw only 4 cards out of the 10? We would be dealing with variations. We should always know how many objects we have and how many selections or allocations we have. So let's say I'll draw 4 from 10 cards. As we see, we can select or allocate any 10 of these cards, then 9, then 8, and then 7. After 4 draws, we're out of picks. We stop there. That gives us 10 times 9 times 8 times 7. We call this number our variation. Variation differs depending on the number of objects and the number of draws. It would be efficient if we were to write this in a factorial form, wouldn't it? Can you think of any other way to describe this product? Let me help you out. Wouldn't it be nice if that could be written as 10 factorial? Imagine the number of ways to draw 4 cards from 10 in order, followed by arranging the remaining 6 cards. The total number of ways to arrange all 10 cards is 10 factorial. We can split this into 2 parts. The ways to arrange the first 4 cards are variation, and the ways to arrange the 6 remaining cards, which is 6 factorial. Using the product rule, variation times 6 factorial should be 10 factorial. So to find the variation, we need to divide both sides by 6 factorial, giving us variation is equal to 10 factorial divided by 6 factorial. If we expand our factorials into products, we can see that cancelling out the numbers yields our original product again. We can also rewrite the 6 factorial as 10 minus 4. Hopefully you can see the 6 factorial was just the factorial of cards minus the picks. Therefore, if we rewrite our 4 picks as p and the total number of cards as n, we should get the general formula for variation. If we pick all the cards, we get 0 factorial in the denominator. You might think 0 factorial equals 0 and be worried about dividing by 0, but by definition, 0 factorial equals 1, because there's exactly one way to arrange nothing, by doing nothing. By adjusting our formula, we obtain our previous formula for permutations. Permutations are just variations where you select or allocate all the items. Ring permutation. In our previous examples, we placed objects in a straight line. But what happens if we place them in a circle? How will the number of unique rings change? I'll let you think about it. Let's say we have 5 gemstones: blue, green, red, pink, and white. If we arrange the gemstones in a ring, rotating the ring produces 5 different views. But we consider all the rotations as the same unique arrangement. That means the number of unique circular arrangements is fewer than the linear permutations. We divide the number of line permutations by 5, one for each possible rotation, to get the number of unique rings. Imagine first arranging the gemstones in a straight line. We already know there are 5 factorial ways to do this. That means multiplying 5 times 4 times 3 times 2 times 1. So the number of unique rings is 5 factorial divided by 5. After cancelling out the 5, we get 4 factorial, which is 4 times 3 times 2 times 1. In general, if we have n items, imagine arranging n gemstones in a straight line. There are n factorial ways to do this. Then we tie the line into a ring. When we tie the line into a ring, we can hold on to any one of the n gemstones as a reference point. Rotating the ring around the gem doesn't create a new arrangement, so we divide by n, giving us n minus 1 factorial unique rings. Now let's add one more idea. What if we also consider mirror images flipping the ring over as being the same ring? In that case, each unique view has a matching mirror view, so we should divide by 2 afterwards. Therefore, the general formula for unique rings can be either n minus 1 factorial or n minus 1 factorial divided by 2. Which one we use depends on the inclusion of mirror images or not. You might even try thinking about ring variations instead of permutations. I'll let you explore that. Now let's focus on another upgrade of our formulas before we dive into something more complicated. Generalized permutations. Until now, our formulas have assumed that every item is unique. This assumption can be problematic when we intentionally add 2 of the same item. To resolve this, we need to think everything is distinct at first. After the grand reveal, we look at the identical items. Notice that if we mix them up, we still have the same permutation. It's like shuffling 3 identical cards. They swap places, but nothing really changes. If we calculate the number of different ways we could permute the duplicates, then we know what to divide by. So you divide the total number of permutations by the total number of permutations of the duplicates, because those swaps don't actually create new arrangements. If we have multiple groups of duplicates, we go group by group, dividing each time until we find the proper amount of permutations. For example, the word consensus has 9 letters, amongst which are 3 S's, 2 N's, 1 C, 1 O, 1 E, and 1 U. If we had unique letters, we would have 9 factorial permutations of these letters. If we look at S specifically, we can permutate those in 3 factorial ways, 2 N's in 2 factorial ways, and the single C in 1 factorial way. Remember, dividing by 1 does nothing, therefore we can ignore the single letter groups. We got our final answer of 9 factorial divided by 3 factorial times 2 factorial, or after calculations, 30,240 new words by jumbling the word consensus. Combinations. We already discussed permutations and variations, but perhaps you've noticed that I avoided saying the word combination. In combinatorics, the word combination has a strict meaning, which I'll explain after recapping the difference between permutations, variations, and the newly added combinations. Permutations are the number of ways you can select or allocate all the cards when you care about order. Variations are the number of ways you can select or allocate some cards when you care about order. In the new combinations, you have the freedom of choosing the number of cards, like in variations, but you don't care about the order. Let's see why order sometimes doesn't matter. Imagine you and your friends are picking 3 toppings for a pizza out of 10 choices. No, you cannot add the same topping twice. Whether you choose cheese first, mushroom second, and olives third, or olives first, cheese second, and mushrooms third, you'll still end up with the same pizza. What matters is which toppings you choose, not the order you choose them in. Again, that's selection. In allocation, we imagine it as placing items in 3 indistinguishable places. Here's a comparison of allocation between permutations and combinations. How do we obtain the formula? We can start with a variation of n items and p pigs. We can imagine that the p selected items can be arranged in p factorial different ways. However, since order doesn't matter, we divide by p factorial to avoid counting the same choice multiple times. Thus, each combination has p factorial ways to mix them. So the combinations times p factorial equals variations of p out of n, or c equals v divided by p factorial. Let's make this formula more concrete. We can express variations using factorials. V is n factorial divided by n minus p factorial. Dividing by p factorial gives n factorial divided by n minus p factorial times p factorial, which is the formula for combinations of p pigs from n items. Sometimes we can write it in these brackets, which translate to n choose p. There are a few tricks that reveal themselves. Essentially, there are several ways to rewrite combinations. We call these combinatorial identities. I'm going to highlight 2, but there are many more. For example, for n items, choosing p is the same as not choosing p. Sounds contradictory, but it isn't, trust me. Not picking p means we choose n minus p to be part of our combinations. If we put this into the factorial form, we can see we can manipulate the formula to derive the formula for n choose p. Here's a second identity that shows another interesting property of combinations. The combination of n choose p is the sum of n minus 1 choose p and n minus 1 choose p minus 1. How would we go about this? Let's put our n items into the set x and choose all except for 1 to be part of set y. Thus, x has n items, while y has n minus 1 items. The item that is in x and not in y will be our target. Either the p choices will include the target or not. Therefore, we can divide our problem into 2 paths that we can sum together. Target not chosen. We can then conclude all the p choices were in the set y, so we need to find out how many ways p choices fit into n minus 1 spots without considering order. Reminds you of something? We can write that as n minus 1 choose p. Now we should quickly move on to the alternative, which is target chosen. That means one of the choices will be the target and the rest will be in the set y. Since the choice of the target is guaranteed, we only care about the combinations of the p minus 1 choices in set y, which can be expressed as n minus 1 choose p minus 1. In the end, we sum up the formulas of these 2 possibilities to obtain the final formula. This specific identity is known as the Pascal identity. We can create an interesting pattern from it, which can help us in other problems. Pascal's triangle. Let's examine n choose p. We already know what we just interpreted it as, but let's consider them as coordinates for now, where n is the row and p is the column. Our n and p can be any whole number that is negative, since you can have -1 items or choose -2 items. In such cases, we will consider them to have 0 combinations. Starting with the upper left corner at 0, 0, we can calculate that there is only one combination. I would also like to note that it doesn't make sense to choose more items than we have. So when we have p greater than n, then we also define it as 0. Therefore, the rest of this row will be zeros. Surprisingly, we can obtain the remaining numbers by using Pascal's identity. To reach a square, add the value above it and the one to the top left. Since n-1 means we have to move it to a row with a smaller value, and p-1 to a column with a smaller value. We can then slide the shape to the right to create a new row. We can continue building rows indefinitely, but this is enough for now. We can move this triangle into its often depicted form. There it is, the Pascal triangle. You are right to question the usefulness of this, apart from being able to quickly find the number of combinations just from reading this triangle. We can discover more properties of combinations. For example, notice these diagonals. Each has an interesting sequence that I could discuss further in the future. Though, more importantly, look at each row. If we were to sum up each row, we get the sequence 1, 2, 4, 8, 16, 32, 64, and so on. Computer scientists might recognize that these are the powers of 2, or respectively 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, 2 to the power of 3, and so on. There's a perfect explanation for that, which brings us to the use of the Pascal triangle. The binomial theorem. Some of you might recognize that a plus b squared is a squared plus 2ab plus b squared, but how would you find the general formula, for example, for a plus b to the power of 5th? Would you multiply all the terms? There is a quicker way. Imagine we expand our expression. We get 5 brackets of a plus b. In each bracket, we are free to choose to multiply either variable a or b first. So we have 2 choices. Then we should do the same thing for the second bracket, the third, the fourth, and so on. We have 2 choices for each and we use the AND operator, so we should multiply the number of options. So we get 2 times 2 times 2 times 2 times 2, or 2 to the power of 5th. So, if we expand a plus b to the power of n, we should get 2 to the power of n terms. Alternatively, if we add up like terms, the coefficients should add up to 2 to the power of n. That gives us a connection to the powers of 2 in the Pascal triangle. But you are perfectly fine not to accept that explanation yet. To get a complete understanding of the connection between the term expansion and the Pascal triangle, I should ask, for example, how many of the terms a to the power of 2 times b to the power of 7 are there in the expression of a plus b to the power of 9? Firstly, I'd be interested to check whether it makes sense for the term to be there. The 9 in a plus b to the power of 9 means how many choices we should make, and a to the power of 2 means we choose a twice. You can't select anything if the exponents, or how many times you choose a variable, don't add up to the total number of choices you were supposed to make. It shows that you either didn't choose completely or you made a choice that wasn't there. The abundance of the word choices here may have sounded a few alarms. Can we use combinations to describe this expansion? Yes, we can. How many different ways can you choose A twice out of 9 times? 9 brackets choosing 2? Sounds like we should look at 9 choose 2. That would mean we have 36 of the terms A to the power of 2 times B to the power of 7. Could we have chosen to look at the number of combinations choosing B 7 times out of 9 instead? Yes, we could, and it would lead to the same calculation. Remember how I said choosing P times is the same as not choosing P times? We concluded that picking P is the same as picking N minus P, which would correspond to our A and B cases. Alright, that was a mouthful. Can we generalize it? Yes, we can. We can. For A plus B to the power of N, it is the same as adding up the terms. We can express them as A to the power of P times B to the power of N minus P, where P is the number of times A was chosen. We replace the numbers with P using the summation symbol, indicating the range of choices. At the bottom, we indicate what P starts as. At the top, we indicate the limit. We know that A can be chosen up to N times, and more would be nonsensical. We also know that we can't select less than 0. We should also add a coefficient to each term. It's a combination of N choose P. We refer to these as binomial coefficients, and there it is. This is the condensed formula for A plus B to the power of N. Although the big picture emerges when we expand it fully. No summation, no brackets. For example, A plus B to the power of 2 is A to the power of 2 plus 2ab plus b to the power of 2. If we add coefficients of 1 before a to the power of 2 and b to the power of 2, we get this. If we only look at the coefficients, does this remind you of something else? If you were to say the row of a Pascal triangle, you'd be right. If you expand and order terms of the expanded binomial, you have the coefficients that appear on the triangle. Impressive! Let's also notice how symmetrical it is. That is, again, because of the identity N choose P being same as not choosing P. However, some of you might be interested in trying solutions such as x plus y plus z to the power of 5. How would we solve that? Unfortunately, Pascal's triangle lacks in this sense. We'd have to use a different tool, which we will focus on now. Generalized combinations. After a long time, we could categorize items into multiple groups, not just chosen and not chosen. Each of the groups has a limited size that has to be filled. For example, let's imagine you are supposed to split 10 types of candy among the 3 of your friends. Let's say they are people A, B, and C. Each has to take 3 candies. That's fair. We can put the last one to the side. The question is, how many different ways can you guys split the candy? In our case, I would like to be going one by one and fill up the groups separately. You have to pick 3 out of 10 candies. You don't want to bother with order, so you declare the first 3 belong to A, the next 3 belong to B, and the last 3 belong to C. So in alphabetical order. Again, it doesn't matter if C or B gets candies first. It's just supposed to help us solve the problem. Since you don't care about the order of chosen candy for A, you can say you have 10 ways to choose 3 candies for A. It doesn't matter if person A eats M&Ms or Skittles first. They only care that they have them. There should be 10 choose 3 ways to give them candy. Now, the rest of the group is left with the 7 remaining candies. B comes along and you pick 3 out of the 7 candies. So now we multiply by 7 choose 3. We'd repeat this process until we reach the last group. In our case, just person C remains, where we multiply by the last 4 choose 3. In the end, the answer should be 16,800 ways. If we have a total of n items and each group has a capacity of C1, C2, and so on, we can calculate it like so. This formula could be further improved with additional tweaks. For example, this nasty bracket is the capacity of the remaining blocks. That would be this blue block in this scenario. So we can write CR, capacity of remaining, instead of this bracket. Sometimes we don't have any remaining blocks, so we can express its capacity as 0. Here's the cool part. This formula is essentially the same as the generalized permutation formula. Why? Because in generalized permutations, we are allocating distinct items to distinct positions, or equivalently, assigning items to specific groups. Whether you think of it as which candy goes to which friend or who owns which candy, the counting works out the same. So we can mostly use generalized permutations or generalized combinations, since they go hand in hand. Why the formulas are the same is something you can think about more yourself, but not now. I bet you're interested in the multinomial theorem. So let's talk about a plus b plus c plus d to the power of 15, for example. And we want to know the coefficient of a to the power of 3, b to the power of 2, c to the power of 6, and d power to the 4th. We should check if the exponents add to 15, like with the binomial theorem problems. I'll tell you that it does. Let's imagine dividing 15 brackets into 4 groups. Groups of brackets that contribute an A, B, C, or D. We know we should contribute to each group the same number of times as its exponent. So only 3 brackets should go to group A, 2 to group B, and so on. Essentially, those are our capacities. We can use our general combination formula to get the multinomial coefficient of that term. These give us the combinations of adding brackets to group A, group B, group C, and group D. Calculating this, we get 15 factorial divided by 3 factorial times 2 factorial times 6 factorial times 4 factorial. That equals 6,306,300 ways, our multinomial coefficient. So if we were to expand a plus b plus c plus d to the power of 15, we would find 6,306,300 a to the power of 3, b to the power of 2, c to the power of 6, and d to the power of 4. Repeatable permutations and variations. You may have noticed that the main limitation of the formulas is the fact that we assume all elements appear a limited number of times. What if we assume we have an infinite quantity of each element? We can allocate or select the same element again as if it magically appeared in the deck. How would that change the overall formula? First, let's talk about permutations. Whatever we pick, we have the same number of remaining options to select or allocate. If we go with the idea that we can pick the same number of elements as there are spaces, then if we have n items, we should select them n times. Although this time we don't multiply our way from n to 1, we multiply the variable n times. That gets us n to the power of n. Variations are the same, but we don't select n times. Instead, we pick the amount of picks. Let's call that number p. So we have n options for p times. So multiplying n by itself p times, we should get n to the power of p. Can we obtain a similar formula for combinations as well? Repeatable combinations, balls and urns. Combinations with repetitions are where it gets interesting. Imagine you are ordering 12 ice creams and you have to choose from 5 flavors. It doesn't matter how you order them, but it does matter how many of each flavor you have. You can order multiple of the same flavor. How many different orders can you have? Firstly, we imagine the 12 slots of the ice cream. Whatever ice cream flavors we pick, we should sort them. For example, let's say chocolate flavors are first, followed by vanilla, and the other flavors. We don't care about the order, but the idea. It'd be helpful to find where the chocolate flavors stop and where the vanilla flavors start, since that can change from order to order, right? How do we get that information here? Visually, we can create a divider between the different flavors. The first section will always be chocolate, then vanilla, and so on. If there were two dividers right next to each other, then we know there's no ice cream of that flavor. Currently, the dividers are in separate locations, but how about adding slots for them? We now have 12 plus the number of dividers of slots. Suppose we remove the ice creams and dividers. Notice that we can place the dividers randomly and determine the flavors of the ice cream for each slot. The first section is always chocolate, so every ice cream up to the first divider is chocolate. Since the dividers are indistinguishable, we can ignore their order. How about we select the divider amount from the 12 plus divider slots, where the dividers will be located. There will be the combination of 12 plus dividers, choosing dividers, right? We're almost there, but we need to know how many dividers there are. Well, we know the number of flavors. Let's imagine a rope we want to cut into 5 sections. You only need 4 cuts, since each cut produces a new section and we already start with 1 section of rope. Therefore, our calculation should be 12 plus 4, choose 4, or generally, p plus n minus 1, choose n minus 1, where there are p items to pick from n types. Again, we can modify the formula to serve a slightly different purpose, but we will stick with this one. So, we had a lot of formulas, right? Let's compare them. We have permutations, variations, and combinations. Permutations use all items and care about order, while variations allow us to use any amount. Combinations allow any amount as well, but we don't care about the order. However, each one of these formulas has a simple, general, and repeatable formula. We will conclude this chapter with this table and proceed to the pigeonhole principle. The pigeonhole principle. Fans of my channel are already familiar with this concept, since it's among my favorite topics in discrete math. I've already made a video about it, but briefly, if we have n plus 1 pigeons flying into n pigeonholes, we are guaranteed that one of the pigeonholes will contain at least 2 pigeons. Or generally, if k times n plus 1 pigeons fly into n pigeonholes, we are guaranteed to have at least 1 pigeonhole with k plus 1 pigeons in it. That sounds obvious. If not, I've created a very detailed video on my channel. Please be sure to check that video out in doubt. Though what makes this principle special through its simplicity is the fact that it is a powerful tool for proofs. It helps you reach conclusions you would typically need surveys for. For example, I can guarantee that there are at least 2 people in New York City with the same amount of hair using this principle. The population of New York City is about 8.5 million. A human can have 0 up to 150,000 strands of hair. The population is the pigeons, and the number of hairs is our pigeonholes. There are at least 57 people with the same amount of hair. The trick is to find out how many times the population exceeds the number of categories. In our case, it's above 56. This 56 would essentially work as our k in the definition of the pigeonhole principle. So 56 times 150,000 plus 1 people divided among 150,000 groups based on their hair ensures a group of at least 57 people with the same number of hair. We can prove something more interesting as well. Did you know that in a group of 6 people, you are sure to have either a group of 3 people who know each other or a group of 3 people who are all strangers to each other? Imagine you are one of the people. Since you see a group of 5 people who know or don't know you, you are sure to have at least 3 people who belong to the same familiarity category. Let's take those people aside and examine the relationships between you and them. Red means unfamiliar and blue means familiar. If I draw this diagram, it seems as if there is a familiarity between these 2 people. It'd make a triangle. which is our group of 3. Let's try to avoid it by saying they don't know each other. We'd have to do this between the remaining edges, but doing so creates a bigger triangle of unfamiliarity. It's the same if you had people you didn't know instead. Using the pigeonhole principle, we prove something about a set of numbers that have yet to be discovered completely. For example, we don't know how many people you need to guarantee a group of 5 that consists of people who exclusively know or don't know each other. Another helpful tool aside from the pigeonhole principle is pi. No, not the cake, nor the constant, but the principle of inclusion-exclusion. I hope you are familiar with the Venn diagram. All the points that are in the circle belong to set A, and outside of it don't. The same goes for set B. Some points are under multiple circles. Let's say we want to count the number of points. If we know the number of points that are in set A and set B, we can add them together, right? Well, not quite. Look at the middle points that are in both sets. You added them twice to the total count, even though they only appear once. Instead, we have to subtract the number of points between them. If you count them twice, subtracting the amount between them prevents you from counting the points in the middle twice. Let's count on this example. How many points are there? This might sound overly complicated, but it helps us generalize this for other types of problems. Let's try having more circles now. In each area, I'll add how many times it was counted. Add all the sets. We can see that we need to subtract the overlaps of 2 circles. Doing that leaves us with 0 on the intersection of all 3 circles. Therefore, we need to add them to the final count to correct the issue. So we added, subtracted, added. This pattern continues forever. Adding can be understood as including the set, and subtracting as excluding elements from it. Thus, the inclusion-exclusion principle perfectly sums up its name. For example, let's imagine this scenario. At a summer camp, students can sign up for 3 workshops: photography, robotics, and drama. 30 students signed up for photography, 25 students signed up for robotics, 20 students signed up for drama, 12 signed up for both photography and robotics, 8 signed up for both photography and drama, 6 signed up for both robotics and drama. Only 4 signed up for all 3 workshops. The question is, how many students are there in total? I'll put the problem aside for a moment and draw the Venn diagram to help visualize it. Here are circles for photography, robotics, and drama. So far, we haven't counted any numbers in the diagram yet. Let's start by adding the number of students in each workshop. Photography has 30, robotics has 25, drama has 20. When we add these numbers, we're counting every student in their respective workshops. But some students are counted more than once because they signed up for multiple workshops. Next, we subtract the students in 2 workshops: 12 for photography and robotics, 8 for photography and drama, 6 for robotics and drama. By subtracting these, we eliminate the double counting of students who signed up for exactly 2 workshops. However, when we subtract these pairs, the student who signed up for all 3 workshops end up being subtracted too many times. In fact, after the subtraction, the triple overlap region counts as 0, meaning those students aren't counted at all. That's why we add the number of students in all 3 workshops, which is 4, back once, to include them completely. Putting it all together, the total number of students is 53. Now that we've seen how powerful the principle of inclusion-exclusion is, we can use it to explore some other fascinating concepts in combinatorics. One of those concepts is derangements. Sometimes you ask yourself, how can I mess that up? Well, derangements will give you that answer. You may have envelopes with their respective messages. You don't want to put each message in an envelope. Instead, you do it at random. Maybe John's message gets delivered to Margaret. We want to pull a prank and hope everyone gets the wrong message. How many different ways could I mix it up so no one gets their original message? So in other words, how probable is it when randomly mixing? The answer lies in derangements. All the possible mixing shouldn't be a concern since we take the messages as they come into our hands. But some of those mixes might be partially correct. We don't want that. We know that the number of derangements is the difference between the number of permutations and the cases where any message reaches its intended recipient. We write derangement similarly, but instead we put the exclamation mark before the variable. So derangements of n are equal the factorial of n minus c, where c is the number of partially correct cases. How do we find how many of c there are? Let's discuss. Firstly, let's draw a Venn diagram for all the permutations. The cases contained in this box should be n factorial, but we need to divide the set into subsets where some person gets the correct letter. For example, this will be our circle for person A got the right letter. Now we add the rest. For now, we suffice with A, B, and C. Now we need to find the number of scenarios between them using the principle of inclusion and exclusion. How many ways can we fix the letter to its rightful recipient? We have n people, currently 3, and we're choosing 1, so n choose 1. We just need to choose an owner. You now have the remaining letters to mix and match. In each of those combinations, you have n minus 1 factorial ways to mix up the rest. You might be asking yourself if mixing won't include a permutation where 2 letters are fixed correctly. That's possible, but that's why we use the principle of inclusion and exclusion. So to ensure that the permutation is counted only once, we add this term based on the principle of inclusion and exclusion. Now that we've counted all the permutations with 1 letter correct, let's move to 2 letters being correct. We need to pick 2 out of n recipients, so n choose 2. The rest of the letters will be permuted amongst themselves, so n minus 2 factorial. Since we added our previous term, we have to subtract this one. Remember inclusion-exclusion. We would continue until we had to choose more fixed letters than there are envelopes. So our last term has to be n choose n times n minus n factorial. We don't know if the last term is positive or negative. It depends on what n is when considering inclusion and exclusion. Now, this expression isn't exactly clean. Can we make the term somehow easier? Now that we examine one of these terms, we can rewrite the combination number in factorial form and cancel out the n minus k factorial. So each term is in fact n factorial over the factorial of a number. Thus our whole expression is. This expression totals the number of permutations of letters that are at least partially correct for n letters and envelopes. Let's remind ourselves what we need this for. The number of derangements is the difference between the number of permutations and the number of partially correct cases. Now that we know how many cases are partially correct, we can substitute that for c. Thus we get this expression. Now we can remove it from the brackets and we can factor out n factorial from the right side to get this expression. There's this nasty string of numbers over there that can be approximated. There's a number, a constant to be exact, whose powers can be approximated. E is Euler's constant, and this long expression can approximate e to the power of x. You can notice both expressions share the factorials and the denominators. You might argue there are these powers of x and not negatives compared to the original. Well, we can substitute for x, but the question is, what x can we use to get the expression above? Firstly, we want to get 1's in the numerators instead of x. That means we can substitute 1 for x. Since 1 to any power is 1, we almost get the same expression. We only need to get the negatives there. Okay, let's try again. What if we substitute a negative number instead? Negative numbers raised to odd powers will be negative, and those raised to even powers will be positive. That would help us create that pattern of plus and minus. Aha! How about we use both? A negative number and a 1. X minus 1, x equals minus 1. Substituting that produces the exact pattern we have above. Now we know that this pattern is approximately e to the power of minus 1. That is, 1 over e, where e is approximately 2.718. The problem is the number of terms in the expression, because that determines the accuracy of our approximation. However, we can discuss these expressions further at another time. I'll reveal that this approximation is more than 99% accurate for n greater than 5. Now we have both the original formula and the approximation. An interesting fact that stems from the approximation is that derangements have roughly the same probability regardless of the numbers of items to be deranged. If I divide n factorial on both sides, I get the derangements of n divided by n factorial, which means the ratio between derangements and permutations. Notice that the right side is just a number. 1 over e is approximately 0.368, which is equivalently 36.8%. Putting that into real-life perspective, if you randomly match definitions to answers on a school test, there's always a 36.8 chance that none are correct, and about 63.2 chance that at least one is correct, with a big enough test question that is. This fact applies to a large enough number of definitions and answers and remains unchanged even when we add more questions. Quite inspiring for upcoming tests. And that's where we will stop for today. We've progressed from basics of sets to the fascinating tools of combinatorics. There's always more for you to learn. I have a number of similar videos on my YouTube channel, such as this one about the Pigeonhole principle, which includes a simulation. Currently, I want to continue exploring combinatorics and investigate generating functions to see how they help us count. Make sure to subscribe to stay tuned for more math content coming your way.